All right, let's get started. Today we are going to talk about recursions. These are what we are going to talk about today. First, we're going to discuss what recursive functions are, and then we're going to talk about a special type of recursion, that is mutual recursion. And we're going to have a look at what are the differences between recursion and iteration. And we are also going to have a look at a special type of tree recursion. And I'm going to present some examples and then summarize this lecture. All right, let's talk about recursive functions first. So what are recursive functions? In general, recursion means to define something in terms of itself, such as the definition of a tree. So when we define a tree data structure, actually it is another type of data structure we're going to talk about in the following lectures. When we define a tree, we define tree in this way. A tree consists of a root node, which is connected to the roots of 0 or more trees. So when we define a tree, the definition of tree contains the term tree. So this is how we define something in a recursive way. So basically a tree is looks like this. So a node is connected to other nodes like this. In computer science, a recursive function is a function that calls itself in the body of that function. Then why do we care about recursive functions? Recursive functions aim to solve given problems by splitting them into smaller or easier subproblems. So some of you might have heard about divide and conquer. So what we want to do is, rather than solving the big problem at once, we're going to split the problem into smaller ones. And step by step, we're going to solve that big problem. All right, that is the spirit of recursive functions. And sometimes these easier subproblems are actually the same problems, but in smaller or easier inputs. Then what we can do is, if the problem is small or simple enough, then we're going to solve it directly. And this is called base case in respect of computer science and recursive functions. And if the given problem is not small enough, then what we're going to do is divide the given problem into one or more simpler instances of the same problem, and pass these smaller problems to the function itself, assuming that it will perfectly manage the smaller problems. So what we need to be careful about is how we divide the given problem into smaller ones and pass those smaller problems to the function without thinking that it's going to work well or not. We just trust that it will perfectly manage the smaller problems. And the beauty of recursion is we solve just small problems and let the function handle the rest of it. All right, let me give you an example. How can you print a number in base 8? For example, what is 83790 in base 8? We know how to do this by hand, right? We write down this number here, and we divide this by 8, and we find the remainder, and we do the division again, and find the next remainder, and we keeps on doing this, and write the remainders in sequence, and that is going to be this number in base 8, right? We know how to do this by hand. And how can you implement this functionality with computer or Python? It is quite easy to find the last digit of a number n in base 8. As I told you, we just divide this number with this 8, and then we find out this remainder, right? And finding remainder in Python is simply using this percent operation. It will simply give you the remainder. And the remaining digits, after we calculate this remainder, what we get is n/n8. This will not think about the numbers after dot, like floating numbers, right? It will always return in integers. And let's implement this function together. So what we want to do is print some numbers in base 8 when we are given a specific number n. And what we do is, if n is larger than 8, we're going to print base 8 and pass the remaining numbers. Else, what we are going to do is print n%8. We put this extra parameter here, and this will print our numbers in base 8. All right. So what is this parameter means? I'll explain this part first. When we print some numbers in a row like this, then after this print function prints out this parameter, it changed the line. So when we want to print out the next one, 8, it printed out on the next line, and 9 on the next line, like this. However, when we put this parameter, pass this parameter to this print function, what it does is, rather than changing the line, it just remains there. And the next print function will print out the character or text given on the next position, like this. All right. So when we call this function, we'll print out we should not put else here. The number in base 8, right? So this is how we implement this print base 8 function. So what we basically did is we find out the base case. So the base case is this one. So if n is, so here the base case is n is smaller than 8. So when n is smaller than 8, we just print n. That's all we need to do. And if n is larger than or equal to n, then we divide this number by 8 and then pass this number, the remaining one, to the print base 8 function itself. All right. So this is the base case, and this is how we divide our big problem into smaller one. All right. So why does it work? Let's prove the functionality of print base 8 by mathematical induction. And here, K denotes the number of digits. So first, the base case is when K is 1. We have just one number of digits. And as I told you, this corresponds to the case where n is smaller than 8. In this case, print base 8 prints one digit correctly. And we want to prove that this will still work even when K is larger than 1 or n is larger than or equal to 8. And we make the inductive assumption that print base 8 works correctly for numbers with less than K digits. If we call print base 8 n, then it recursively calls print base 8 and /8, right? So this is the definition of our print base 8 function. But n/8 has K minus 1 digits in base 8. And by the inductive assumption, we assumed that this function works correctly for these numbers. So this will work correctly. Finally, we print out the last digit, right? Thus, it follows that print base 8 prints n in base 8 correctly. All right, so this is how we prove the functionality of this function using mathematical induction. All right. So up to this point, are there any questions? All right, let's move on. So let's implement factorial. So what is factorial? N factorial is simply n times n minus 1 times until we reach 1, right? So this is simple operation. And when we try to implement factorial, some of you might implement the factorial function in this way. And do you think this will correctly work or not? Let me know your opinion. All right, so why doesn't it work? Yes, you gave me the right answer. So when we try to call this function, what it does is, let's say when we call factorial 3, then what it's going to do is return, because n is 3 now, 3 times factorial n minus 1, that is 2. And this f2, when we call this f2 function, it will return 2 times f2 minus 1, that is 1. And f1 is going to be 1 times f0. And f0 becomes 0 times f minus 1. And it goes on and on. So it does not stop because there is no base case. So you guys are getting this right. And what about this one? Does it work well? Think about it for a moment. I'll give you 30 more seconds to think about whether this one is correct implementation or not. All right, thank you for sharing your answers. Hayne explained gave the right explanation, because when we try to run this function, what it does is call the factorial and again. So it cannot reach this base case. So even though it has this base case, it cannot reach this base case because we are not decreasing n. All right. So this was pretty simple, right? Thank you for sharing your answers. And let's think about summing digits without a loop. So for instance, if we have number 2022, then summing digits might be 2 plus 0 plus 2 plus 2, and that is going to be 6. And how can you sum up all the digits without using any loops? Can you implement a function for this? So for example, let's say we have a function that receives a number so when some digits receive 2022, it's going to return 6. Some digits 2023, it's going to return 7. So can you implement this function? Think about it for a moment.